Hi, in this work, we propose an object-centric recovery framework to address the challenges of out-of-distribution scenarios in visuomotor policy learning. Visuomotor policy has proven to be a powerful paradigm. By directly mapping visual inputs to motor actions, they eliminate the need for explicit environmental modeling and streamlines the deployment of new skills onto robots. However, current visuomotor policies suffer from distribution shifts, which can significantly limit their ability to generalize to unseen scenarios. For our running example, we present a well-trained, state-of-the-art visuomotor policy that has been trained exclusively with the object initialized on the green shaded regions of the table. In this setup, the policy performs as intended, lifting a bottle and placing it onto the red plate. We've referred to this as our base policy. Next, we modify the environment by placing the object in the red shaded region, which lies completely out of the training distribution. This shift creates a severe out-of-distribution scenario, resulting in the base policy struggling to complete the task. Thus, to recover from these object out-of-distribution scenarios, we propose the object-centric recovery framework. We will now walk through the critical components of this framework. Firstly, OCR estimates 6 degrees of freedom poses of target objects using off-the-shelf estimators, then converts these poses into object keypoints. Then, having these object keypoints, OCR estimates the probability density distribution of keypoints in the training data by fitting a Gaussian mixture model. Next, when the objects are out of distribution, which is decided by a probability density threshold, OCR calculates the gradient of the training GNM with respect to the current keypoints, forming the object recovery gradient and the object recovery trajectories. Lastly, using the keypoint recovery trajectory, we obtain the robot actions by calling the keypoint inverse policy. The keypoint inverse policy takes in desired keypoint motion and translates it into the robot actions necessary to complete those keypoint motion. This inverse policy is learned purely from the object and robot interaction that existed within the base training dataset. Using the OCR framework, we can now recover from unseen object out-of-distribution scenarios without the need of additional data collection. In our experimental results, OCR demonstrated a significant improvement, enhancing the base policy's performance in out-of-distribution scenarios by 77.7% across the 3 task environments that we tested on. In addition, OCR can be used to automatically provide data augmentation for regions with low object density, enabling continued training on the base policy. For the push T task, we utilize OCR to automatically collect 100 out-of-distribution demonstrations, resumed training with the augmented dataset, and observed improvements in both in-distribution and out-of-distribution performance. If you're interested in learning more about our project, please use the QR code to visit our project page.